With their vicious appearance and large size, sharks can evoke great fears, like something out of a nightmare. But are sharks really the human-eating monsters many perceive them to be? Studies have shown increases in the numbers of shark attacks on humans. But a likely reason for the increase in shark attacks is the increase of people at beaches and in the water. It appears that as the beach attendance rises, so does the number of shark attacks. Here's a plot showing the number of tourists in Florida in given years versus the number of shark attacks there in the same years. This is an example of a correlation between two variables. The value of one variable is associated with the value of another. Scatterplots are a helpful tool to show a correlation between values of two variables, as well as the strength of those correlations. But observing a correlation raises another question. Is a correlation due to variation in one variable directly causing variation in the other? Or is the association coincidence, or caused by variation in a third variable? For instance, if the temperature for a certain number of days was very high, and automobile sales were also high on those days, you might observe a correlation between the two. But a correlation does not necessarily mean that one of the correlated events, processes, or conditions directly causes the other. Is hot weather the reason more people buy cars? Not necessarily. If correlation implies causation, we could just as well say that greater car sales caused hot weather on a certain day. Clearly not. Correlation does not imply causation. But if people buy more ice cream because the weather is hotter, temperature will be correlated with ice cream sales. Causation does result in correlation. Let's look at some examples of correlation and how to identify and interpret them. Every summer, sun seekers flock to beaches. The beach is one of the most popular vacation destinations around the world, and for good reason. There's nothing like feeling the sand between your toes or catching that wave in the surf. But what fun would the beach be without warm weather? This chart shows a sample of the daily temperatures at a particular beach and the number of beach goers for each corresponding day. Are these two measurements related? If the value of one variable is systematically associated with the value of another, if the variables vary together, then the two variables are correlated. The degree of association, or correlation, can be visualized by plotting the data on a graph. In this case, the sample of temperatures versus the number of beachgoers on the same day. If a scatter plot is only to assess correlation, the question is about the association of the variables. So it doesn't matter which variable is graphed on the x or y axis. However, when a correlation is used to check consistency with a hypothesis of causation, the variable thought to be causing the other is typically represented on the x-axis, and the hypothesized response variable on the y-axis. Each data point is located at the intersection of the values for the two variables that are paired. If the temperature was 86 degrees for a day on which the number of beachgoers was 515, the point on the graph for this pair of values will be where x equals 86 and y equals 515. These two values are the coordinates for that point on the graph. Once all the points are plotted, you can analyze them based on whether and how the plotted points appear to be associated. If the points form an elongated pattern at an angle in which both variables increase and decrease together, up to the right and down to the left, as these variables do, the variables are said to have a positive correlation. You can see from the graph that as the temperature increases, so does the number of people at the beach. This is an example of a positive correlation between these two variables. If one variable tends to decrease as the other increases, the two variables are said to be negatively correlated. The pattern of plotted points will be oriented down to the right and up to the left. If the variables do not appear to be associated, that is, no pattern oriented at an angle up or down is apparent, then the variables are not correlated. For example, if you plotted the outdoor temperature on the days of math tests against a class's average math test scores on those days, you might expect to get a graph something like this, in which no correlation is apparent between the two variables. So what if you do have a correlation between two variables? How can you determine how strong that correlation is? You can figure this out by calculating the correlation coefficient. The correlation coefficient, typically represented by the letter R, is a number between -1 and +1 that expresses how closely and in what direction the variation in two variables is associated. This is reflected in how well the data points in a plot of one variable against the other line up diagonally, and which way the pattern slopes. If R is greater than 0, the correlation is positive, and the pattern will slope up to the right on the graph like this. The closer the value of R is to 1, the stronger the positive correlation is. If R is less than 0, the correlation is negative, like this. The closer the value of R is to -1, the stronger the negative correlation is. If a correlation is weak, the value of R will be closer to 0, like this. The formula for the correlation coefficient R is straightforward, but involves several quantities. Many calculators can calculate it. Scatter plots are a useful tool to help determine whether two variables are correlated or not. They show you whether and how variation in one variable is associated with variation in the other. Ah, the sounds of the beach. Good weather can help make a day on the sand perfect. This scatter plot shows a correlation between two variables, air temperature and the number of beachgoers. As you can see, there appears to be a positive correlation. As the temperature increases, so does the number of beachgoers. The trend of the data can be described by plotting a line of best fit through the data points, like this. Now that we have a line of best fit for the data, we can measure the rate of change for the data using the slope of the line. The slope for this line is 15.4. It means that there tends to be an increase of about 15 people going to this beach for every increase of 1 degree in temperature. But as you see, it's variable. Now what happens if you were to change the scale of the graph? Would this change the results? When the scale of the y-axis is increased, you can see that the displayed data pattern changes to a narrower appearance, making the variables look more closely associated. The displayed angle of the data trend and of the line of best fit also change. But when calculated, of course, the slope remains the same, and the correlation is the same because it's the same data. You can get an impression of the correlation from graphing the data and observing how well associated the variation in the two variables is. But the actual correlation is a characteristic of the data, not the graph. The scale of the graph is irrelevant to the actual correlation. Here, you can compare the impressions provided by graphs of some data with different degrees of positive correlation, with the displayed axes covering roughly the full ranges of the data. No matter what the degree, the use of a scatter plot is a good way to illustrate a correlation between two variables. For many, living on the beach would be like living in paradise. Because of this, oceanfront property is a hot commodity in the real estate market. Suppose that recent sales trends have shown an increase in prices for oceanfront properties for a particular region in the past year, and that the construction rate of new oceanfront homes in the same area has risen. By plotting these two variables together, one against the other, ignoring the months, you can show that there appears to be a correlation between the price of oceanfront homes and the construction rate of new oceanfront homes in the area. But remember, a correlation doesn't mean that a change or level of one of the variables causes a change or level of the other. Correlation does not necessarily imply causation. Once you've found a correlation, it's important to analyze the meaning of the data and interpret it if you want to understand what's behind the correlation. Is the price increase in oceanfront properties causing the increase in construction of new oceanfront properties? Maybe, but there could be another source of influence on property prices and construction rates not included in the graph, which has affected one or both of the variables. This is called a lurking variable, one not taken into account in the experiment or observation. For instance, what if there's been a rise in the overall economy of the area? More business is bringing more visitors to the beach and subsequently more home buyers. The likelihood of a lurking variable in this situation, the overall economy, suggests another explanation for the increase in prices with an increase in the construction rate, other than a direct causal relationship between the two. Changes in both could be due to changes in a lurking variable. Graphs and correlation coefficients are useful to identify correlations between variables. But be careful, the appearance of a correlation does not necessarily mean that changes in one variable directly cause those in another. Your analysis should always return to the meaning of the variables and consider whether some other explanatory variable is lurking. Alternative explanations should always be considered.